here's how, you know, your walkie-talkie transmits an electromagnetic wave, is that, remember that same antenna we talked about last time you could tune for receiving, right? You could just make this, say, a wavelength or half a wavelength or 2 wavelengths or something like that. And then a dipole antenna, what it does is it just oscillates back and forth. It makes this negative and that positive, and then, you know, another cycle later, this is positive and that's negative. And the electric field in between here is oscillating back and forth. Well, here's the crazy thing. If you've got an electric field, right, and you get rid of it, if you take away the thing to make it, electric fields contain energy. So it can't just go away. It can't just like disappear. The energy in that electric field has to go somewhere. Well, where does it go? Well, it turns out that when an electric field collapses, it creates a magnetic field perpendicular to it. This is one of Maxwell's laws. And the magnetic field looks around just like Wile E. Coyote when he runs off the cliff, right? And he says, hey, there's nothing here to make me. There's no magnets, right? And so the magnetic field collapses. Well, magnetic fields contain energy, and when they collapse, they create an electric field, which creates a magnetic field, which creates an electric field, which creates a hungry crocodile. I'm sorry. Okay. So anyway, that's the idea, right? Is that, and so then the question is, where can electromagnetic waves travel? Well, they can travel anywhere you can have a magnetic field or an electric field, which means they can travel through a vacuum. These are non-mechanical waves. They can travel through glass. They can travel through water. They can travel through air. They can travel through nothing, right? So these are crazy, crazy waves that way, right? Okay. And they travel, if you're in a vacuum, they travel at a speed that is a physical constant of the universe, the speed of light, which is, with 3 sig figs, blah, 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 blah. With 3 sig figs, it's 3.00 times 10 to the 8th, right? If you have 4 sig figs, it's like 2.998 or something like that, right? And then the weird thing about the speed of light is that because it's a fundamental constant of the universe, it's independent of the speed of the source or the observer. So if I turn my flashlight on and I shine it at Kevin, Kevin sees the light coming toward him at the speed of light. If he runs at half the speed of light toward me, he sees that light from my flashlight at the speed of light. It's blue though. If my flashlight was like white looking, it would actually be blue shifted, right? But he'd still see it at the speed of light. Okay. Now if I ran toward him at 3/4 the speed of light with my flashlight and he sat still, he wouldn't see it at 1 3/4 the speed of light. He'd see it at the speed of light. This is a weird thing, and the reason for that is, of course, if the speed of light changed, then magnets would change when you moved. Yeah. And Einstein back in 1905 said, no, that doesn't make sense. Magnets are going to work the same way if they're moving at a constant speed. So therefore it's light that's weird. Light is weird. Yeah? Isn't that weird? That's weird. Is that weird? That's not what we expect, is it? Yeah, we don't expect that. Sound doesn't work that way. If you shout from that side of the room and I move half the speed of sound toward those waves, because sound travels through air, I see it at 1.5 times the speed of light, or sound, right? Yeah?
So it's the different color, that's from the frequency, right?
Yeah, it's because when you travel, you actually, your dimensions shift, and yeah, it's like length contraction, stuff like that, right? Okay. And then there's a whole spectrum of electromagnetic waves. Radio waves are, microwaves are, infrared is, light is, ultraviolet is above that in frequency. We're increasing in frequency. X-ray, right? What's happening, by the way, to the energy of these things as we go to higher frequency? Are radio waves safe? Yeah, they're fairly safe, probably pretty safe. It's safe to hold a cell phone up to your head and talk for a long time, maybe, right? Probably, right? Okay. Infrared, well, that, you can heat somebody up with infrared. Light, I don't know. Ultraviolet certainly gives you a sunburn. X-ray, the person walks out of the room when they give you an X-ray. Doesn't that worry you? It's like, no, you stay here. You stay here. With the scary thing. No, because they give like 40 X-rays a day. You get one every other year, right? Okay, and they cover up your, they're basically covering up your reproductive organs is what they're doing. Because that's the greatest danger, is that, especially women, because you've got, I think don't you have like all the eggs are there right now? Isn't that right? Is that right? Yeah, and so if we're like knocking DNA strands out with X-rays, that's bad, because, right? Okay, and then gamma rays, you can just expose a whole room full of meat, ground beef to gamma rays, and it'll kill everything in that room. The beef is already dead, but it'll also kill like the E. coli and all the other bacteria, right? So what?
What are
Gamma rays are just really high frequency light. Yeah? It's the same thing. There's a high frequency electromagnetic waves, right? Light is just what we call the stuff we can see, right? Now,
Is there anything faster
then light.
than gamma rays?
Oh yeah, I mean, they just keep going, right? At some point, I don't know what you call them, right? You know, there are these things that have the energy of a fast-pitch baseball that hit the Earth's atmosphere. They could be photons, right? But we think they're actually just protons, high-speed protons. Yeah.
What exactly is a frequency? I don't make sound.
Frequency is how many waves go by you a second, right? So if it's like 440 hertz, it sounds like a violin string. Yeah. Not the rate of travel, but the rate of up and down. Yeah. So there is actually a cheer that we do. Do we know this? Do you know this cheer? It goes like this, and I want, you know, we've been sort of quiet here, but I want Mr. Youngberg's class to know this too, don't you think? Because those kids might take physics too, right? Okay, so it goes radio waves, microwaves, infrared light, ultraviolet X-ray, fight, 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 gamma rays, physics. That last part is kind of a little a cappella. Yeah, are we ready for this?
Yeah.
Radio waves, microwaves, infrared light, ultraviolet X-ray, fight, 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 gamma rays, physics.
Let's do that again.
Yeah, I think we need to. A little bit louder though. Radio waves, microwaves, infrared light, ultraviolet X-ray, fight, 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 gamma rays, physics. Usually they've got like some. No, we've been obnoxious enough. Usually they'll respond. Sarah will respond with some sort of a cheesy little biology thing too. You know. There it is. So this is I won PowerPoint of the year in 2003 for this slide. Watch this. So these are, we're going to put some here and here and here, but there are no longitudinal electromagnetic waves. So mechanical waves, shear earthquake waves, the S ones, they make the Earth's crust look like an S. They're not called that because of that. They're called that because of the shear force. Shear is like shears, right? It's like part of it's going this way, part of it's going that way. It's how you tear paper, right? Waves in guitar strings are transverse. I'm resisting saying ocean waves. Nope, no, I didn't resist it, right? Those are the mechanical transverse waves. Right, here's just examples. And then examples of longitudinal waves. Well, there are S and P waves. P waves are the pressure waves. Those are the ones that cause changes in pressure, so those are longitudinal. And both a disturbance in the Earth's crust will create both of these kinds of waves. Yeah? Sound waves are all of them longitudinal waves, right? A compression wave in a spring, the thing that I dropped the little bow tie thing with, right? That's a longitudinal wave, right? And then surface waves on water, all electromagnetic waves, right? The whole cheer. Radio waves, microwaves, infrared, light, ultraviolet, X-ray, fight, 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 gamma rays, yeah, physics. I just demonstrated a technique. I've already told you what to do with the solicitors.
No.
When somebody calls you and you really don't want to talk to a solicitor, but you know it's a solicitor, you can play games. One game you can play this is a simple thing to start off with, but one game you can start with is the dude game. All you can say to the solicitor is dude. Once you know it's a solicitor, you're honor bound to say only dude, but you can of course inflect dude all you want, right? So, Mr. Murray, dude. You know, I'm calling you from the siding company, dude. You know, dude, right? And you want to keep them on the line as long as possible.
We do this?
Yes.
How long have we done it?
Well, I kept somebody on for like 2 minutes, but I sort of felt bad because at the end they're like, "Are you there?" You know, I don't know. There's more complex versions of this. You can try the Pledge of Allegiance.